Let us explore another way to find out the derivative of x to the power n. If you remember previously in the last video what we did, we found out that d by dx of x to the power n would actually be nothing else but n x to the power n minus 1, and we did it by using the first principles method. Let us now use another way to find out this derivative. So let's assume this x plus change in x is some number a. Let us just assume that this change in x plus x. Okay, so that means my new x equals to a. Okay, let my new x equals to a. So what does that mean? That means that my change in x is nothing else but the new x minus old one, so a minus x. Okay, so now as change in x would go to 0, what does that mean? That means that a minus x goes to 0. A minus x goes to 0 actually means that a is almost equal to x, right? So that means that a tends towards x. Okay, so now my difference quotient, let us again figure out the difference quotient that we have been looking at, the change in f upon change in x. What will that be? That will be f x plus change in x minus fx upon change in x. Now this is equal to a, right? As I've assumed x plus change in x equals to a. So this equals to a. So in terms of the function x to the power n, okay, f of a would be a to the power n, and f of x would be x to the power n. So the difference between a to the power n and x to the power n is something that we have to figure out, right? So f of a minus fx upon a minus x, change in x is essentially a minus x, right? Now consider the following, consider a to the power n minus x to the power n. Now a to the power n minus x to the power n would actually equal to the expansion which is a minus x, that comes out into a to the power n minus 1 plus a to the power n minus 2. The power of a decreases and the power of x increases. Here you had the power x to the power 0, here you have x to the power 1, so on and so forth. The power of a is decreasing, so it becomes a to the power 1 here, and this is increasing in terms of n, so this becomes x to the power n minus 2 plus x to the power n minus 1 a to the power 0. Okay, now why do I have from n minus 1 to n minus 1 here? That's because I have taken out a minus x. Okay, so when I multiply this complete with a minus x, that will essentially give me a to the power n minus x to the power n. Okay, so now using this expansion, let me now look at my difference quotient. My difference quotient now becomes, my difference quotient becomes del f upon del x, which equals to as following. Now what will happen here? This and this will cancel out. A minus x will cancel out from numerator and denominator. Okay. Now what will remain is the powers of n minus 1 and lower. Okay. Now next what will happen? Next what do I have to take? I have to take the limit as change in x tends to 0, which means that a tends to x. So if a tends to x, then what will happen essentially? I will rather have all x's here, right? I will have, in place of a, I will have x. So I will have x to the power n minus 1 plus x to the power n minus 2 into x, and so on and so forth till x into x to the power n minus 2, and here anyways I don't have to replace a. So that would essentially, when everything is getting multiplied, what will it give me? It will give me x to the power n minus 1, again x to the power n minus 1, because what will happen is that the powers get added. So n minus 2 plus 1 will give me n minus 1, and so on and so forth till n places. These are all n places. Okay, this will happen in all n places. So n times x to the power n minus 1 is what we get as f dash x.